Hi, today we come back to continue with the von Thunen model. So, the last lesson stopped with an exercise on the von Thunen model. I hope you have spent a little bit of time on finding the answers to question 1 and question 2 of the exercise. Today, let me walk you through a standard answer for such exercise. Firstly, to answer question 1, we need to recall the distant decay mechanism and the location rent formula. The distant decay mechanism said that when the transport costs increase, and location rent will increase. And the location rent formula is LR, which is location rent, is equal to Y times M minus C minus T times D. Y is yield. It's a constant on the table, as you can see. M is the market price, C is the cost of production, and T is transport cost per unit of product. And M, C, and T are not going to change during our calculation. In other words, they are constant, just like Y, the yield. So if D increase, then we will have LR decrease and the other way around. So question 1 asks us to allocate crops, which means we make an order of the crops to maximize economic benefit. Accordingly, we need to find the highest transport cost product to put closest to the city center or the market. That would be crop A, transport cost per unit 200. Then we'll go for the second highest transport cost unit product, which is B. And we have B should be put next to A, just after A. And then D50 is the third highest, and C is the last one. So the correct order, or as we often say in here, is the initial order for question 1 would be crop A closest to the city center or to the market, then B, then D, then C. So the answer to question 1 is crop A, then crop B, crop D, and crop C. Let us continue with question 2. Identify DI, which is D1, D2, D3, D4, or DA, DB, DC, DD, which is the distance of the crops. How big is the size of the farm allocated to each crops? In order to find the answer of D, we need to again recall the location rent formula, and we need to find the intersection of the location rent lines. Let's look at the graph. The brown line here is crop A, and we need to draw the line, and it's too easy. I don't have to explain to you again because it's a linear function of LR and D. The intersection, this is line B, the orange line, So we will switch from crop A to crop B at the intersection of line A and line B. So we need to find the intersection of line A and line B. Let's move on to the next slide. Okay, in order to find the intersection between line A and line B, which is the location ran of crop A and the location ran of crop B, we need to put them together in one equation. This is the first equation. X here stands for dA. At the intersection with line B, so dA equal to dB at that point. Okay, and by solving this equation, we'll find out that X, which is D1, is also dA according to your denote, and it's also dB at the point. It's equal to 2.5 kilometers. So it's the point where we will switch from crop A to crop B. We'll plant crop A from the market to the to 2.5 kilometers away from the market, and we'll switch from there to crop B. That's how we explain the result. And then from crop B, when will we switch to crop C or crop D? In this case, we will switch to crop D first, right? That's what we and then we want to find the connection between line B and line C. And we have the same thing to do. Then the connection between line C and line D. We have the same thing to do. We put them together and find and solve the equations to find the intersection. But the tricky point of this exercise is that in question A, we found out that we should go from B to D, not to C, right? So we will switch from B to D, but not to C, because the transport cost per unit of crop D is higher than the transport cost per unit of crop C. So we would tend to put D closer to the city center. So instead of looking for the intersection between B and C, we actually have to look for the intersection between B and D. And we haven't been able to find the intersection here because we didn't put this formula here. That's the tricky part that I put in the slide. So you need to be very careful when you see this kind of question because it might be tricky, and you have to check if question A and question B are connected. So as we already found that we should switch from B to D, then we need to find the intersection between B and D, and we put this equation equal to this equation. Then we'll find the answer is, in fact, 13.3 kilometers from the radiation, from the city center. So it is in fact that we will switch from point. So what can we do in this case? In such case, my suggestion is that you need to draw the graph. And actually, in all exercises like this, you'll be asked to draw a graph of the lines. And from the graph, you can easily see what's going on. where you should stop planting one crop and switch to the other, and what's going on with the numbers. Since you cannot see in the graph, it's really hard to judge if you really want to switch or not, or if you really want to follow the initial pattern in question A or question 1, or you need to change the initial pattern. In this case, the graph would look like this. This is line A, this is line B, the orange line. Line C would look like this, and line D is the gray line here. So we can easily see that line C cut line B before line B can cut line D, which is this point. So this point is before this point. If you look from left to right, this point is before this point. And that explains why we see the intersection here is from the calculation we can find this is 5 kilometers, this is 2.5 kilometers, and this intersection is 13.333 kilometers from the radiation from the city center or from the market, and so because we are aiming at maximizing the location range, we always choose the highest location range possible, which is wherever the location range, the highest point we choose. So we should go like this, go from here to here, and here to here, and then here to here, which means that we will switch from A to B, and then B to C, but not to D, right? Not to D. So the initial farming pattern in question 1 that we found should be changed. So it's not always true that we should follow the initial farming pattern, but we need to follow the location range, the highest location range possible. So in this case, we would choose to switch from plant B, crop B, to crop C at the point of 5 kilometers from the market. And then we keep planting it because location range of crop C is still the highest over here in this area. It's still the highest. Let me show you. Here it's still the location range. So we go from crop A to crop B to crop C, right? And this point is 5 kilometers. This point is 2.5 kilometers, and this point is supposed to be 13.3. And instead of switching from B to D, we actually earlier we already switched from B to C. So from here to here, you can see that the location range is always the highest compared to other location range down here. So we always choose plant crop C to plant until we reach the maximum, which is the boundary of the farming area, which in this question, in this exercise, is 38 kilometers. So we will stop farming until this one reach 0, or we will stop farming until the 38 kilometers radiation. So the answer to this question is actually 2.5 and 5. And we would not plant crop D because simply it provides lower location range comparing to switching from B to C. So that's the answer to the question. I hope you understand it, and let's practice a little bit more with another question. This is a longer question, and but in fact, question A and question B is very similar to what we have just discussed. Question C, the same thing, but just only one change. Transport cost of crop A and crop B reduced by 30%. So this one is just 75. This one just 40. And we have to do the same thing as what we have done with part B to find the answer. Do you plant all crops, or do you just plant 3 crops or 2 crops? And in order to answer that, you need to do the calculation again. And then D is illustrate your result on the graph, but actually we, as I mentioned, we usually do it beforehand. So it's before doing any calculation, we better draw the graph to see what's really going on. And then we can judge if we can really switch to one crop from one crop to another, or we stay on with the crop that we are having, or we even switch earlier than the intersection that we predicted. And then question E, the von Thunen model is of course an oversimplification of reality. Mention two important or discuss two important limitations of this land use model, and that is a very good connection with what I'm going to tell you in the next slides. In the next slides, which is the modification of von Thunen model. Some modified conditions of von Thunen model. So in 1826, von Thunen already noted down some important modified condition of the model. First, different places possess different physical factors, and we all know that, because there's no place the same to the other. Second, large town markets do not often lie on a navigable river or canal. Third, product costs are nothing simple. Product costs can be changed, and it might be another variable, but not a parameter as we had in the exercise. Competing markets, so the price can be changed over time. But in fact, in this von Thunen model, this is the simplest von Thunen model. We assume that the price doesn't change. And in some cases, farmers do not maximize profits. And this part I already explained in the last lesson. There are many farmers that just follow each other, and they follow what they believe, or they follow their preference. They don't do economic analysis or market analysis to see what is really the most beneficial choice. They just follow the neighbors, farmers that they can see that's earning benefit, and they just plant whatever they want. So in fact, in reality, is harder for us to judge what's going on. The modified conditions listed by von Thunen also help us to see why the land locations, the lands allocated to the crops are not like rings as we discussed in the von Thunen's model, but they are chains. And there are some other modified condition here, and you can always read in the book, in the textbook, to understand more about them. And there are actually more and more modified conditions found during the advancement of research and the development of reality. Technology, yes, we have fridges which will have help us reduce the transport cost, because we will have less fruit ruined by higher temperature. We have fridge, but of course we still have to pay for electricity, so the cost still there, but it's much lower than without the fridge, since we don't have to lose the fruit or the food if we don't have fridge. Change over time. There are many different factors that can be changed over time, like political impact. Like we have a new policy that people cannot go from part A of the land to part B just because they are not allowed to by the government. So then the cost will be changed. 8. Emerge of special regions characterized by a particular type of agricultural land use. We have agricultural land use might be changed because we have many different types of agricultural land, and due to the climate, they can be changed. One example is the Mekong River Delta. We see that it's changing rapidly, quickly recently, and there are a lot of, but in fact there are a lot of factors belong to our neighbors like China and the upper Mekong River Delta countries that we cannot control. So the specialized regions characteristic might be important in our calculation, but we for now in this simplified model cannot include. Cooperative productions. So one crop might affect the other crops as well. If you put crop A next to crop B, it very might be that crop B would be better than if you put crop A, and then if you put crop C next to crop D, for example. So they might be supporting the others in the production. Impact of the government policy, as this is similar to point 8 that I have just mentioned. 11. Freight rate in reality is not directly proportional to distance, but it's step-shaped or being divided into different freight rate zones. This is obvious. In reality, you know that we have different freight rate zones, and there are many other factors that can change the freight rates. And because of that, the rings, as you can see on the left here, can be changed to not ring anymore. This is the case where we have a river flows through the city center, and because the river would reduce the transport cost, one farmer who stay here, for example, can choose to go straight to the river and then take the river to the city center. It is still cheaper than going just on land straight from where he is standing to the city center without the river. So by because of the appearance of the river here, the rings will be changed. The rings will be changed like this, and the river, you can imagine that the river would expand the city center. So the river flow to here, from here to here, then it's like we have many other cities lines along the river here. So farmers here can choose to approach the cities prime here rather than here, because he knows that from here to here, going along the river, water transportation would be the lowest transport, will reduce his transportation costs significantly. So that's one modified condition, one example. Or there's another secondary market, apart from the first market here, the primary market. Then the whole thing here would be changed as well. So it's a very interesting modified condition of the von Thunen model, and you can always see this happening in real life. This is the case that we have one center city here, but we have some subsidiary towns here, and that will change the rings. It lower the transport costs, and there are many others, examples of the modified condition that you can always read more on the slides and in the. And this is, I just want to show you this because this is the real thing happening. This is Argentina, Buenos Aires, and this is the real von Thunen model modified. So they modified the von Thunen model, so they are not rings anymore, like perfect rings, but they are still have ring shape like this, not perfectly round, but still one inside another, and we have some particular areas allocated to some particular crops. So that's still following the von Thunen model, and because they can use some very sophisticated software to illustrate the von Thunen model and to include the modified conditions in the von Thunen model, and they can predict the shapes of the land. They can predict if this area would be for, let's say, commercial grain farming. They can predict that, and this is what you can really observe in reality. Actual types of agriculture, it's a bit different to the modified von Thunen model. Why it is different? Because we cannot include every modified conditions, because we are still looking and we are still researching for some more modified condition, because the reality is so complex, so complicated. So we cannot include everything in the model, but in fact, they look really similar to each other. This area is still for commercial grain farming. This area is still livestock ranching, and this area is still dairying. Market gardening is still here. Just a little bit of change here. Probably we have something here that reduced the no, that increased the transport cost. So it's not sensible to have market gardening here. And the city center here, Montevideo, is the point, is the central market. So it's very interesting to see this in real life, and see how the von Thunen model can be applied in farming planning, and also urban farming as well. You can see this in if you have a look at the state map as well, the location of the products here according to the assumption, the von Thunen model, and this is real life. They are different, but there are many commons in the in the farming pattern. And you can always see more details here. So if it'll be a good idea if you look at the graph and try to figure out what it is, and try to answer why the crops are planted there. And this is corn for grain or seed by country. By county, in the state we have many counties, and some counties are specialized in some products. And the von Thunen model can be applied in urban planning as well, and it can get very complicated. Firstly, it's not linear relationship anymore. It can be like non-linear relationship, and the basic of the von Thunen is developed as a mid-range theory applied to urban areas, urban planning. Um, this is like one example of the non-linear line, and this is an advanced question for master student. If you going to study higher, then you will definitely face this kind of questions. And we have some applicable applications of von Thunen model in designing inner city living and suburban living here. So, but as you can see here, it's very interesting that the CBD with commerce and offices always stay in the city center. Industry will be a bit further out, and residential with highest density nearest center would be here. Um, and because this area is very condensed, we would wish to have skyscraper, the tall buildings, to have more people in, to be able to allocate more people in the inner city to reduce the transport cost. And that is the idea, the first idea, to explain why we have many tall buildings in the city centers, because we can put more people in such a small amount of land, and by doing so we can reduce the transport costs. And this is another example in the state Houston. You can see this and try to explain what's going on in here. And this is the end of von Thunen model. I hope you have got the idea of the von Thunen model. Again, this is the simplified von Thunen model, and we are just learning the idea of it, but not the complexity of the model. But still, it can lead to some difficult exercises that you and I will be discussed in the class, and also we would practice a lot in the class, try to find the answer to some advanced questions. Look forward to your questions, and see you next time. Enjoy.